I'm a professor of machine learning, which is a sort of a related area to statistics, but I thought I'd start off with a little bit of controversy for this old quote. There are three types of lies: lies, damned lies, and statistics. It's an overused quote, but it's striking how often people don't actually know when the quote was made. Does anyone know who the quote is accredited to and what year? Pardon? Mark Twain doesn't credit to himself. He writes it, but he credits to someone else. So that's in 1906. Pardon? Disraeli. Thank you, Disraeli. Benjamin Disraeli is credited as saying that. Now, one of the important things about that is Disraeli died in 1881. So the Royal Statistical Society, I think, is founded in 1834. 1837 is the electrical telegraph is sort of invented. And Disraeli presumably governed an empire where he was getting pretty sick of various types of statistics misrepresenting what was going on. So one can imagine if he did say it, as Twain credits him as saying, so you want to imagine quite why he did say it. Now, I think that the important thing is, the most important thing from my perspective is the launch of mathematical statistics. So there's lots of other things, or the most important thing for this meeting with the LMLS, and of course Carl Pearson. So, press the wrong thing there. Carl Pearson, so who of course founded what was one of the first departments of statistics, and is seen as the father of mathematical statistics. And of course the important thing about mathematical statistics is it's ensuring those lies aren't told. It's a way of looking at the stats and ensuring that what's said in the statistics is credible. And I think that that's one of the most important innovations in modern society in terms of keeping in check claims that are statistically invalid. The ideas that Fisher, of course, was a key figure, Egon Pearson, Jerzy Neyman, all these people developed in order to protect us against those lies. Now, the problem is people just remember the quote. They don't remember that it was kind of dealt with. But I think that that puts us in a new and interesting era, because I'd say today the relevant quote would be, there are three types of lies: lies, damned lies, and big data. The reason I say that is because we're moving into this sort of new era where data is becoming sort of omnipresent and omniprevalent, and people are starting to look at data and deal with ways with the same sort of naivety that people would have dealt with data, well, enthusiasm and naivety. I mean, lots of good things were done in the sort of mid-19th century around data, and lots of interesting things are being done today, but we're back in this sort of Wild West world of people playing with data at a very large scale. And why do I think it's different? Well, I think, first of all, it's absolutely vital that we address this. And I don't know necessarily what data science will come to mean. As I think Peter hinted, what is science without data, or data without science? So it's in some sense, it's a nonsensical term. But in another very important way, it will hopefully represent something which might be akin to the mathematical statistics that Pearson did so much to develop, that ensures that we are protected against the lies of big data. So just a sort of bit of background to that. I mean, data is a sort of pervasive phenomenon. It affects all aspects of activities. One of the most interesting things of working with data is you can kind of broadly work in any field, as many people here know, I'm sure, because you can just choose a field where they generate data that's interesting and you can work in that field. But the diffusiveness is a sort of challenge and an opportunity. Now, what I think is that there's been an evolved relationship, and I want to represent this relationship in this way. So this line here, I thought that was that doesn't do a pointing. Ah, that's why, it doesn't actually point. So this line here represents what I think people were trying to explore in the 19th century, the relationship between human and data. So in the beginning, there were humans or data, and then together you can misrepresent data and you can persuade a human that something's going on where it isn't because we have certain inductive biases. And mathematical statistics was about this link. Now what's happened is that's a fairly narrow bandwidth link, but the development of digital computers has led to a very high bandwidth link between data and the computer. So this is a little trilogy. You've got the human, the computer, and data. And you've got this very rapid now link between between data and the computer. Humans are still bandwidth limited. I'll come back to what I mean by that in terms of their interaction with the computer. But there's now far more opportunities for corruption and misrepresentation of data because the computer is seeing so much more of it, and the computer is interpreting the data before it's presented to the human. Thus the challenges for big data. So this is the sort of new flow of information that's going from data through the computer to the human. And that's why I think that this is not just a matter for business as usual. This is a matter for us to come together with joint meetings like this and have good, serious thought about what the new issues are when you insert this new entity into the channel, because it has the opportunity to manipulate what we see. Okay, so I have this thing that I think of as embodiment factors, and these are very rough figures because actually representing human computation ability in flops is probably nonsensical, but the table here is trying to show you the difference between the ability of a computer to compute and communicate. So on the left, we've got how much a typical desktop could do is about 10 gigaflops in terms of computation. And a typical network at the moment would be about a gigabit per second. Now, a flop will be a 64-bit operation, but roughly speaking, let's divide one into the other, and we see that you get a factor of 10. So in other words, the computer is, roughly speaking, to within a couple of orders magnitude, computing 10 times more than it can communicate. So it has a little bit of a backlog of its compute. Now, estimating, this is Claude Shannon, estimating Shannon's computational ability is hard, but you see various estimates that if we were to simulate a human brain, how much compute we'd require. Now, I saw another recent estimate that says, it says recent estimates you see are sort of around about an exaflop. And so that's not quite within the range of our fastest supercomputers today, to real-time simulate human brain, about an exaflop. So 1,000 teraflops, and our ability to communicate this is probably an overestimate, but in terms of verbal communication, you can see estimates of about 40 bits to 60 bits per second. I'm not including visual communication, you'll have much higher bandwidth visual channels, but I think that's interesting. And it means that if you divide one into the other, sort of embodiment of the human being is maybe 10 to the 13. I don't know, it's very large. So we have this massive backlog of computation that we can do, and I think it leads to a large part of the human condition. A lot of what we're trying to do is express ourselves and communicate. This sort of thought occurs to me that, like you trying to listen to me in the room now, potentially you're doing more compute than all the simulations of the climate and the weather, the world across, just trying to understand what I'm saying. And I'm putting an equal amount of compute in trying to produce that for you. So very low bandwidth channel. Now, that means that there's an enormous opportunity to prepare data better for the human in order to show the human, okay, this is how the data is coming in. But it also means there's an enormous amount of perils, because humans have all these inductive biases that come about through this strive to communicate. We cause other things to be embodied. We think of computers themselves as anthropomorphic and everything else. And all these biases are the sort of biases that can catch us out when statistics are being presented to us. Okay. So I think that this phenomenon of this very large data is already, we've got evidence of where this is having effects before. So data science, although it's a sort of more modern term, I think even 15 years ago we were starting to see this phenomenon in biology. We were starting to see the case where you were getting large amounts of data being produced, and biologists who weren't equipped to handle this type of data were having to digest it for the first time, and we had a requirement for new sets of methodologies in order to present that data. So in some sense that's nice, because we've had a dry run, and a lot of the lessons we see from that dry run can be applied here. So large-scale data acquisition and distribution for interpretation by humans who aren't necessarily trained in the analysis of data. Now, this also has an enormous effect on the society around us, and I think we're seeing this in terms of our experience of the world as seen through social media, Facebook, Twitter. There's a lot of automated decision-making going on by algorithms that are being designed by large companies. They're not being designed, I really have to consider the downstream societal effects of this algorithm, because any individual decision by the algorithm is not major. It's not, we're going to spend 100 million on mosquito nets in Uganda and Kenya. It's not that level of decision-making, or we're going to release this drug because it seems to have efficacy. It's, oh, this ad seems to match these people, they seem to like it, or people like this type of Facebook photo. It seems like a minor decision, but it's becoming so pervasive that the accumulated effect of these things is changing our experience of the world. Okay, so I've already, I think, covered that. So what I really wanted to sort of talk about today is 3 challenges that I think arise from that. And I'm going to sort of spend a bit of time on the maths of the first challenge and less time on the maths of the second 2 challenges. The sort of things that we need to address, some of the things. And the first of these is, so I sort of learned that you should always do things in 3s because people can remember that. So there's more than 3 challenges, but we've categorized them in 3 ways here. Paradoxes of the data society, quantifying the value of data, and privacy, loss of control, and marginalization. And these are sort of things, they've been around before, I'm sure, but I think that they're becoming more important because of the increasing importance of data. So the first thing I want to talk about is what I call the breadth versus depth paradox. So it's interesting because we're getting an enormous amount of information about society and about people. We're able to quantify to a greater and greater degree the actions of individuals because the amount of recording they're doing on their sort of mobile phones. But oddly, we seem to be less able to characterize society. What do I mean by that? If you look at large-scale surveys, so if you look at sort of polls for elections, we seem becoming less capable of predicting the outcome of elections. This may be a sort of transient phenomenon because it may be that society is changing rapidly in the experience of data, and therefore our sort of poll weightings that are used for looking deep into society. I'm thinking depth, by the way, in design matrix, so depth is large N, breadth is large P. So what we're getting into perhaps is a situation where the nature of what people do is changing so rapidly, but we can't update our sort of statistical methodologies quickly enough in order to be able to estimate quickly what's going on. But it seems almost like as we measure more, sometimes we seem to understand less. So that seems an odd thing. But I wonder if, first of all, as I say, a greater preponderance of data is making society itself more complex and people's interaction with electrical devices more complex. And traditional approaches, therefore, to measurement are failing. So I think of this as a curate's egg of society, so it's only measured in parts. And if it's measured in parts, it's a bad egg, right? You know, it's bad in parts was the curate's egg example. So another analogy on that, people say you can't see the woods for the trees. So in the data, the trees would be the depth of society, and the number of the whole wood would be the depth of society. And an individual tree is the breadth, large features about an individual tree. But very often, if you're analyzing a forest, you may be interested in the whole woods, you may be interested in an individual tree, but often you're interested in a few trees together and how they're interacting, the little micro ecosystem that's occurring there. So I've mentioned some of these examples already. And I sort of think that a lot of this comes down to the way that we look at statistics in a traditional way, which is broadly speaking as a table. So I've written down a statistical data set here as a table, a design matrix Y, where I've got n individuals, of which I know P features, and therefore I have a design matrix of n by P. And this is the typical type of data set we would consider in statistics or machine learning, indeed. Now, what we tend to think of that as very often is a series of vectors, each of which represents a data point. So I've sort of drawn it in this way. So each vector is now an individual data point, y1, comma, colon. That's a sort of MATLAB notation for that. But we could also think of it as a series of features. So we could also think of the thing as vectors, where each vector is representing a feature for the entire population. And I think that this is important because I think the failure to think of it like this leads to something slightly odd. So normally, in classical maximum likelihood, what we would do is we would make an independence assumption across those individuals. And we condition on a set of parameters. I've used theta for parameters here because in machine learning we use W, and in statistics you often use beta, so I'm using theta sort of between, which I think is quite common in physics. And normally what we try and do is say, well, what's that saying? That's saying that the data is conditionally independent given this set of parameters. Which is nice. And often in statistics, those parameters will have meaning, like about the effect of smoking on the causing cancer or something like that. And of course, we turn it into log likelihood and maximize. Now, the justification for that is consistency in the maximum likelihood sense, such that theta is typically in the order of p, our dimensionality. And we tend to justify by saying the true distribution, capital P of y, is well approximated by approximation P of y given theta in the KL sense, because we can show that this lower maximization is equivalent to a sample-based approximation of minimizing that KL divergence. And that's the classical sort of proof for maximum likelihood. The challenge with it is the quality of that approximation diminishes with lower data. So for large P and small n, this is a problem, because you get a less well-determined set of parameters. And so that's led to the so-called large P small n problem. So for large P, these parameters will be badly determined, and we get a large P small n problem. But there's this odd slight effect that I think is very odd, because this is actually easily dealt with through definition. So what if, instead of defining my model as being independent across individuals, conditional on a set of parameters, I decide to define it as independent across a set of features and correlating across the individuals. So I'm perfectly entitled to do that, because all I care about, certainly my own perspective, is to do probabilistic machine learning, and these just are ways of defining a probability distribution. Now, in this case, the math works out the opposite way. So you can show that as you get more features for a fixed number of individuals, you will get a better determined parameter set, because your parameters now scale with n, yet your information is scaling with p. So I do think it's it's true that large P small n is a problem, but it's not a problem with the data. It's a problem of your model definition and how you're choosing to model your data. Traditionally, we've modeled data in terms of conditionally independent given the parameters across the data points. But there's nothing to stop us doing this. And indeed, you can do it very trivially with Gaussian processes. And those models do work very well in high dimensions when you do that. But there's good reasons why historically we didn't do that, because we didn't design data sets like this. So I don't tend to think large P small n is a problem. But what about P is approximately equal to n? So we have an equal number of things about an equal number of people. So now our parameters are going to scale with P and n. It's a little bit hard. Now you also get things like stratification, populations, batch effects, etc. And I think that the answer for this is actually you have to start thinking about why, for some of these new situations, whether the techniques you're applying are even appropriate for the data you're looking at. If you have your data in a table, that's fine, because someone carefully collected for that reason. But there's an open question: does P even exist? It's a sort of, does it make sense to talk about P? And one of the things I'm sometimes fond of saying is my mum drives a Humvee, right? So who knows what Humvee is? Yeah, or a Hummer. Yeah. So as soon as I say that, you start thinking things about my mum. Is she some sort of madame, or is she a drug dealer? What does she do? Now, I've given you a new P. You didn't know I was going to say that unless you've seen me speak before. It's a feature about me that allows you to perform inference about me, and you're capable of doing this all the time. She doesn't drive a Humvee, she drives a Volkswagen Golf. But if I were to say that, you wouldn't think anything unusual of my mum, because a lot of people drive Volkswagen Golfs. So you can actually assimilate new pieces of information, which we would classically think of as P, and you can make it draw inferences from them, because you think in some complex way that these are interconnected with other things you care about. So what I'd argue is that you have to return to something a little bit more general, the sort of way that if you really were to start thinking about modeling, you didn't know all the history and all the great stuff people have done, you would probably do. Data is not indexed by n and p. Data is indexed by whatever, a spatial location, a time, some whatever labels. I think of it being indexed as, it could be indexed by continuous things, it could be indexed by what I think of as x. And in streaming data, that might be in the Internet of Things, as we keep talking about. That might be a sort of a camera measurement at this location followed by another camera measurement. The data is not going to appear in table. You get a phenomenon, what I would say is massively missing data. So even if you see a data set in terms of a table, you're just seeing a small window on the possible data you could acquire. And most of the time, that's the situation we're faced in. Now, I would argue that what you really want to do, and my notation is Y star, is future things I'm interested in predicting, and Y is things I've already seen. And what you want to do most of the time is try and make predictions about Y star given Y. How you choose to decompose that model is a question for your modeling, but that's the starting point that you should consider. Now, I think that the one aspect you then do need if you're going to do that is that your distribution has got to be Kolmogorov consistent. And I don't know, people are arguing with my little notation here, so I'm not sure how useful it is. But what I'm trying to say is that typically, if I marginalize across a distribution where I'm saying the future things I'm going to see Y star is variable length, so it's length n star, There will always be, and it's going to be a much more complex dependency than I'm illustrating here in the top line, there will always be a dependency on those future things. So a typical joint distribution between y and y star, it's going to matter what the length of y star is, it's going to matter what the distribution of y star is. So I'm just putting that conditioning in by n star. So I need to actually, in general, condition future probability observations on how many things I'm going to see, and I need to know what those things are. But that's not true if the process, the system, the distribution is Kolmogorov consistent. It's Kolmogorov consistent if you can do this marginalization and you don't need to know those future things. So this is the underpinning of process theory. So things like Dirichlet processes, Gaussian processes are all Kolmogorov consistent. They are allowed to be distributions over infinite spaces, which is what you sort of need in these cases. And that's the sort of direction I think we should be thinking in, which I would say is Bayesian non-parametrics. It's a very historically mathematical area. It's been looked at in machine learning and statistics and probabilists. But I think that these techniques probably need to be brought into practice, because if you're going to model streaming data, you're going to have new y stars coming at you the whole time. If you do a design where you have a fixed number of parameters, as I'll argue in a moment, that's going to be a bad thing. So I think that all modeling should really sort of go back to this type of distribution. Let me predict the future given the past, where I try and allow my future to be a variable number of observations. Now, in a parametric model, Kolmogorov consistency is trivial because you can sort of just write down the model. You've got parametric with independence across n. It's not trivial if we have independence across p, which is why you don't tend to see that as much as you see independence across n, because people expect new n, they don't expect new p. So I think of this argument, sometimes I have this sort of thought, the large p small n is a very odd thing to say, because let's say you're working with an ecologist, and an ecologist comes in and says, I've been into the woods, and I've observed 7 species, and I've observed 3 things about them. Well, let's say, let's observe 20 species, and I've observed 3 things about these species. And that's great. You're very excited. You fit your logistic regression or whatever you're going to do and tell him something about these species. Now, the next day, the ecologist is even more excited. I went back into the woods, and I've observed 18 more things about those 20 species. And you're like, damn it, you idiot. You've given me a large p small n problem. I no longer can model the data. It doesn't really make sense. But it's because of the way you were modeling the data. And you didn't expect him to add new features. You expected him to add new species. So you built your model in that way. If you were expecting him to add new features, you would flip the whole design matrix around and consider the features as species, and you would still be able to model it in some interesting way. So parametric models have that problem, but they have this challenge in terms of how you deal with sort of new data out of left field, whether it's p or n. And they also lead to a bottleneck. So I've written down the Bayesian posterior of theta given y. So if at design time we build our model in terms of what we expect to receive in our data, then we select a fixed number of parameters. And that's the maximum. So that sort of gives a bottleneck about how much information we can pass from our training data to our test data. Now, in streaming data, where you expect new data to be coming in constantly, you've made that choice before you observe the amount of data you're going to look at. And so this is a really interesting domain to look at, I think. Okay, so I'm not really going to have time, I think, to go through this too much in detail. But there's a problem with these sort of finite storages, these non-parametric models, because a non-parametric model in this domain implies that you increase, effectively, implicitly, one way of thinking about it is you increase the amount of storage you do as your data increases. So I'm probably in danger of upsetting people with my thoughts on what non-parametric models are, but I would claim a non-parametric model is one where the effective number of parameters, the only way of representing this model in this way would be for theta to increase as you increase the amount of data. That would be my perspective on a non-parametric model. I'm sure there are various ones. But it's sort of clear that in a computer and in a human, you can't do that forever, because now you're going to have to store everything you've ever seen. So this presents a sort of new challenge. Well, okay, the parametric model is great, but if you go non-parametric, you now have to keep increasing the data set size. So with very large data, with big data, you don't tend to see non-parametric models applied, despite the fact that you probably want a non-parametric model because the complexity of the data is increasing as you get more data. So this is one way that we look at this in machine learning, and specifically to do with Gaussian processes, but we introduce inducing variables into the system to help us deal with this challenge. So this is an auxiliary variable set which acts like artificial data. So what we do is we have an auxiliary variable set, which I'll try and illustrate in this graph. So normally, I might have some latent function I don't observe. and then I've got some observations y. Now, I'm going to introduce a new set of pseudo-observations, things I don't observe, which I can sort of make up what they are, because I'm just marginalizing them out in the above graph. So if I can perform this operation, if I can easily invert that relationship, which you can happen to be able to do for a Gaussian process, so that instead of representing the joint distribution as P of y given f, P of u given f, P of f, you can invert that quickly so that you've got P of y given f, P of f given u, P of u. You might prefer to see the graph drawn in that way. Now, the nice thing about this, in these Gaussian process models, we typically integrate out f, but it could be any latent variable model which you're trying to remove. If you integrate out f, so I'm removing, before I integrate out f, I should say, I'm just going to throw away P of u for the moment and look at P of y given f, P of f given u. And then that's removing the P of u. And then integrate over f, I get back to a P of y given u. Now, this long operation is just to show you that I can recreate it in something that looks like P of y given theta. Now, I'm not going to go through the details of how we do it, but basically, if you were to do that operation, it doesn't gain you anything, because you have to consider all data for a non-parametric model in computing your P of y given u. But in variational compression, which is a technique we use to apply to these Gaussian processes, we actually don't consider, we consider an approximation. So when we develop P of u given y, we don't use the true P of u given y, the probability over those posterior observations. We have an approximation that is finite bandwidth. So you think, but now you're just getting back to, the same problem we had before, because that's the same problem with parametric models. You're only going to store u things. But without going into the details, because of Kolmogorov consistency in this case, we can change the number of things we store at runtime. So what we get is a lower bound on the likelihood that is dependent on the number of variables we're including, u. So we get this parametric looking representation, but at runtime we can increase the number of variables we store. And I think that this is a very powerful approach potentially for dealing with these sort of challenges. But it's probably not the only one. The key fundamental challenge here is we want to go non-parametric to deal with all this sort of streaming data in a consistent way, but we somehow have to have the advantages of parametric compression, where we're storing only some things about that data. And I think that that's a really important mathematical challenge. To deal with these sort of challenges, these sort of paradoxes as well, this mid-P, mid-N, we need lots of other things. So one of the things I think people fear is, well, it's going to all be about these algorithmic things and so on and so forth. No, it's going to be nothing like that. So when Xerox actually were looking at the paperless office of the future in the 1970s, they realized they needed to get to graphical user interfaces because no one was going to use photocopiers anymore. And of course, the truth was that the amount of paper consumption shot up through the 80s and 90s as we all started printing all the time. And the graphical, we still, I see all the people around having bits of paper, some laptops. We still aren't in the situation of the paperless office. The same situation with all this data. In order to validate these types of models, this is a modeling framework. So models bring all sorts of subjectivity with them, which can mislead you about what's going on with the data. Now, they can be a help and assistance in trying to understand what's going on, but there's this careful division between exploratory data analysis and confirmatory data analysis. And learning when to wield these things in these new domains is going to be vitally important. So deploying those statistics is key. So larger studies we also need in order to get a better characterization of society, and I think a better characterization of humans and how they behave, so that we can better model. Okay. So the next challenge I wanted to talk on, I'm going to talk less about where I think the maths might come from for these next two challenges, is quantifying the value of data. And I mean, this is an ongoing challenge. I'm sure people have experienced it before, but I think it's even larger now. So the way I like to put it is there's a sea of data around, but most of it's undrinkable. We need data desalinization. Why is it undrinkable? Because it's not curated. People don't do the right things when producing the data. People haven't recorded the right things. They didn't think about it. They just gave you a load of data. I'm sure we've all experienced that. So there's a lot of work required to desalinate that data to try and get it in the right form. A lot of work required getting people to collect the right data in the first place. But there's a major challenge in terms of how we measure value in the data economy. So how do we encourage data workers, people who do curation and management of data sets, which has a very downstream high value effect, but it's indirect? How do we encourage them to do that? It's equivalent to how do you encourage people to repair roads. There's no immediate effect for repairing a road, but it's important societally that your roads are in good condition because there's downstream effects. This is a challenge. So in machine learning, there's something called reinforcement learning, where you have a state of a world I've represented by S, and according to what state of the world you're in at any given point, you get given a reward. So reinforcement learning is used for things like gameplay. So at the end of the game, you get the reward of winning the game, but at an intermediate stage at the start, you don't know what your reward's going to be. So here R may be unobserved, and you choose to take an action. You play a move. So in machine learning, they represent these by very often partially observable Markov decision processes, which are sort of Markov decompositions of the probability relationship. And the challenge with them is at the end, you might get a very serious reward, but which of these actions, these interventions, these decisions you made in the intermediate stages are responsible for generating that award? So that is known in machine learning as the credit allocation problem. So how do you allocate credit for which move in the playing of the game was the important move in the victory? It's a very difficult problem. And the more you think about it, it's sort of the whole of the distribution of money is a credit allocation problem, trying to credit some advance according to who gets the money, who gets paid for doing all these things. Data economies have the same challenge. How do you distribute? Was it the person that cleaned up the data and made the data set available that allowed the app manufacturer to look at an open data set of London cycling to make a very successful app that understood where all the bicycles could be and sold for 15 million? Well, the person that cleaned up the data set doesn't see any of that. You know, that's the sort of challenge we face. So I think this is a really difficult problem, and it's hard because data is extremely difficult to embody. So you can talk about data with people, with decision makers, and say, we've got this data, but they have no sense in terms of what you mean, in terms of whether the data is useful or not. And this is why there's so much rubbish spoken about big data, because it's a great thing. You can be in a company and say, well, how are we going to solve that challenge? Well, it's a big data problem, so we can use a big data solution. And then we're done. We can leave our management meeting and have lunch. But we know from computational biology how important this was. So the Wellcome Trust, I love the, were you actually there, Simon? The Foggy Bottom meeting? It's such a great name for a meeting where things are so uncertain, the Foggy Bottom. So the Wellcome Trust 2010 joint statement for the Foggy Bottom meeting, my slides are online so you can click through on that, is all about sharing and access to data and ensuring that happens so that people can get the conclusions they need. So solutions, I think, are to encourage greater interaction between application domains and data scientists. So we have to get out much closer. We have to have people in application domains who are data aware. We have to have people who are interested in statistics or machine learning but care about specific applications. Encourage visualization of data. So in visualization of a data set in the sort of exploratory way embodies it in some sense, particularly geospatial data sets where you can sort of show these are all the schools and so on and so forth. The better the visualization, you're starting to communicate with the human and give them a sense of what might be possible. The thing I would really love to see, and I had this idea and I searched, and someone has mentioned this idea before, but in a specific context, something like the concept of data readiness levels. So if you think in technology, we often talk technology readiness levels. Technology is difficult to embody. So technology readiness levels are like, I think level 3 is I've tested this thing in the lab and it checked out. But level 7 is I'm ready to deploy on a field trial or something like that. And sort of decision makers understand what these levels mean. Well, what about data readiness levels for where a data set is? You know, data readiness level 3 is someone's actually bothered to look at the data and check that there aren't crazy things going on like minus infinity for missing values or something like that. You know, someone's done a visualization, data readiness level 5. But you need some sort of shared sense of what those levels should be. And there's lots of implications for a centralization scheme. So we do work in Africa, Data Science Africa, where people tend to be looking at how you can extract data from individuals and often using things like mobile money to do that. Okay, very quickly, because I don't really have time. I think privacy then becomes the really final thing. I've got 2 other things, loss of control, marginalization, that I won't talk about, so there's time for a question or so. But going back to how those humans are modeling things, if it genuinely is something like that you have an approximation of some pseudo observations in your head which is induced by the things you've seen in the past, then I have one set of ideas and you have one set of ideas. And we communicate over this very low bandwidth channel by taking a function of what we see and presenting it as data to each other. And we're trying to get a shared understanding of the world. That's what I'm trying to do now. I'm trying to communicate the things I care about and think are important to this as an audience. So I'm saying G of A is equals to U of A, some sort of function of that. It's actually vitally important in this scenario that we control G of U of A. because some things we don't want to reveal. I'm not telling you about my toilet habits, right? Because it's not relevant to this conversation. And if you look at what's going on now in terms of the data that's being acquired about us, it's taking everything. The computer sees it all. We are totally losing control over this channel, and that means that we're losing control over this ability to communicate. It's a very complex process because, of course, within ourselves, we are modeling at some sub-level the conversation itself, and within ourselves, the other one is modeling that thing in order to do this communication well. This is all going on subconsciously and consciously in what we do. It's an extremely complicated process, and what we're doing at the moment is saying, well, let's just give the computer everything about us so it knows everything that we are, and the result of that is the computer can start doing things to us. Like my favorite one is, the idea is, does free will really exist if you discover that statistically computers can predict your behavior better than you can because they've seen your whole internet, Facebook likes and everything else you've done? I don't know. That does happen. There's papers that say, and just using it, I think, a lasso regression on people's Facebook likes or a lasso classification on people's Facebook likes, that you can predict people's behavior better than their friends and their relatives can. Now, you could presumably, if you have enough data, take that to the next level and with very simple models make predictions of people's behavior better than themselves. That's because you are more than the... Oh, damn it. Yes. You are more than... You within yourself, you have a self-model. You have a perception of who you are, and unfortunately, a lot of evidence from psychology shows that that perception is mismatched to reality. We all think we're nicer people than we are. When we're asked about situations that we'd be in, we always say we do the nice thing and we're very generous and everything else. And that's the little model of ourselves within ourselves about how we'd react. It's a very, very complex process, and it needs psychologists and social scientists to come in and help us in understanding that process so we can understand that channel between the computer and the human. Okay, so there's other things there that I think: marginalization, discrimination, digital revolutions and inequalities. So how this process, when you've got all this data, affects people who are on the margins of society. And I think there's a massive condensation. So this is a lady in Uganda in a village about our perception of her life, which is probably also, oh, she's constantly worried about dying of malaria. I don't know what she's worried about. Let her decide how the data determines her life. And at the moment, it's the West that generates all these solutions and sort of is pushing them out there. But the people that could benefit the most from a sort of future data society are probably those in countries with the least infrastructure, because that's where data will really come in and help. So let me just go to my conclusion. So data science offers a great deal of promise, but there are challenges and pitfalls. And it's really incumbent on us as the technologists to foresee them and avoid them, because it's going to be too late. Basically what's going to happen is we're going to hit all these problems and people will say, well, where are the technological solutions? And we're like, well, yeah, we were actually busy doing something else. So we need new ways of thinking. We need sort of mathematical data science. And many of those solutions also require on educational awareness, increasing people's understanding of what they're doing. And so the Royal Society has a big role to play there in terms of when they're dealing with data and the downstream pitfalls of doing so. And that's everything. Thank you.